All right, guys, this is going to be the Chapter 11 notes, video notes here on chi-square tests. So this first page is actually an activity they would normally do in class. So I'm going to skip that for now. And we're just going to go straight to some definitions and stuff, just like normal. So what is the chi-square test? Goodness of fit test, and how is it related to one sample z test for proportions? So we test a claim about the distribution of a categorical variable, not about a parameter. The chi-square goodness fit test is the general case of the one sample z test for proportions. Okay. So the big difference between chi-square and what we were doing before is now we're going to start talking about categorical variables, and so we can kind of expand our definitions that we already know. So what's the null, what's the alternate hypothesis? So HO is the distribution claimed or given values, right? So your baseline. And your HA is going to be, is always not equal to. Okay, so you're going to have a distribution that's equal to some number, and then your HA is always going to be not equal to that number. Okay, and again, always in terms of population. And then your evidence, your observed, so what you observed counts are not the same as the expected counts from HF. So how do you find the expected counts? Well, you've done this before with your binomial. You just take the probability and multiply it by n. This is similar to the binomial where you distribution, which we've talked about before. So you multiply the probability by n, and this is equal to your expected counts. And key thing here is, should you round these numbers? You do not round these numbers. Do not round the expected counts. These represent the average number in each category for repeated samples. Okay, so then what we're going to end up doing is we're going to be testing what we actually observed with our expected values, and then we're going to see if that's going to be significant or not by using this chi-square test statistic. So the test statistic is a measure of how far the observed counts are away from the expected counts. That's what we're going to try to find, and then we're going to use a chi-square table to find the probability. And so chi-square, the equation, you have this kind of fancy x is equal to the sum of then you have observed minus expected squared. So your observed value minus the expected value squared all over the expected value. Couple things. This is on the formula sheet. Make sure you use expected counts and not proportions. So in a goodness of fit test, when does the chi-square distribution or chi-square test statistic follow the chi-square distribution? The test statistic follows the distribution when the expected counts are at least 5. So this is a condition. So this is a condition. Your degrees of freedom is equal to the number of categories minus 1. Notice that df is not dependent on the sample size, but rather the number of categories. So what does the chi-square distribution look like? It's going to be a skewed right distribution. Shape is skewed right. The mean is equal to the degrees of freedom. The peak is at degrees of freedom minus 2. And your spread, your standard deviation is equal to square root of 2 times your degrees of freedom. So then how do you calculate these p-values using using the table? So there's a chi-square table on Canvas that you can look at. There's also the chi-square functionality calculator. So chi-square table or chi-square functionality calculator. All right, so that's a bunch of definitions. So now here's a good chance to practice. Okay, so see if you can calculate the expected values. See if you can find the null and alternate hypothesis. See if you can find the chi-square stat, and see if you can make the conclusion based on your p-value. Again, set an alpha level and kind of decide, and go from there. And again, as always, we'll go through this in class together. It's a really good practice problem. So try this out, and yeah, we can move on. So what are the conditions for a chi-square goodness of fit test? Again, a lot of similarities with some of the stuff we've done before. So 1, randomization. Again, it allows for you to extrapolate to the population. 2, you have to have the independence condition. So n has to be less than or equal to 1/10 big N. And 3, we have this large counts condition. Before we were looking at n times p has to be greater than 10, n times 1 minus p. Here, for chi-square, it's all expected counts need to be greater than 5. So again, another good practice problem. See if you can calculate the expected values. You got some percentages here. So you see if you can get the expected values. See if you can then find the sum of the observed minus expected squared divided by expected. Find the chi-square statistic. See if you can do all that. See if you can get a chi-square value. The TI Inspires do have a chi-square function on the calculator, so which again I'll show you when we get to class. And yeah, we'll go from there. It does make it a lot easier because some of the calculations can be quite tedious. So last big thing I want to talk about in this video, when should you do follow-up analysis? So in general, whenever the results are significant, however, on the AP exam, only do what is asked. So if they ask for follow-up, do it. If they do not, then don't. And your follow-up will be to look at the components in the direction of your values of your chi-square. So if you notice that once you're calculating your chi-square, the one specific cell has a large chunk of your total chi-square, then that's part of your follow-up. So that's something you can notice and say. So components and direction. And you can also say something about were there more observed than expected, or vice versa, right? So you can kind of do some little follow-up analysis based on what was found. Okay, so then you can look at large deviations, right? So what cells leads to the biggest impact of the chi-square stat? So that's it for the 11.1 video, just some introduction to chi-square. Again, chi-square, looking at categorical data, looking at more than one thing, related to the one sample z proportion, talked about expected values, and and the equation for the chi-square. We'll look at the specific examples in class. As always, if you have questions, let me know. But have a great rest of your day.